Welcome to qnawire.
Okay. All right. Hello. My name is Jamie, and it looks like that we're given a situation where an incident light is going at the side of this crystalline quartz. And this crystalline quartz would have an internal ray where we go from its incidence to point P. And our goal for this is to find the maximum N of the fluid when the ray undergoes total internal reflective refraction. So that would mean that this angle right here would be 90 degrees. Okay, so to make it easier for all of us, let us label everything right here. So I'll call this theta 1, which was given to us, 34 degrees, and theta 2, and this would be theta 3, and it's 90 degrees, we'll just call it theta 4. So it looks like in this case, this crystalline structure, we'll just name it to have a index of refraction of Ng for glass. And Ng is given to us for crystalline quartz. Ng is equal to 1.544. All right, so we pretty much have all the essentials. Since there are two incidences in this case, we would name this incident A, and this would be incident B. Let's start at incident A. Right here. So as usual, we would use Snell's law on this. Index of refraction N times sine 34 degrees, this would be where the fluid is equal to Ng times sine of theta 2. Okay, very good. I'll just name this equation 1. Okay, now for B, we would have N times sine theta 4 is equal to Ng sine theta 3. Now to find theta 3, actually let's start with theta 4. To go with theta 4, it is given to us, actually we needed it to be 90 degrees for total internal reflection. Now for theta 3, however, we would use the interior angle theorem, that this one would be theta 2 because of the because of the interior angle theorem of this, as you can see over here. And since we know that this would be 90 degrees, theta 3 would be 90 degrees minus theta 2. And we have theta 3. Look at that. Now let's plug everything in. And sine theta 4 would actually be 90 degrees is equal to Ng sine 90 degrees minus theta 2. Let me just circle everything here. There we go. go. Wait, hold on. Let's not circle that just yet, because we could simplify this even further. Sine of 90 degrees is just 1, so n is equal to ng sine 90 degrees minus theta 2. And now we have our second equation. I'll just name it equation 2. All right, there we go. So ng is already given to us, and since we have two equations and two unknowns, which is n and theta 2, this problem is solvable. Okay, so let's manipulate equation 1. Right here. I'll just isolate n. No, actually, I'll just isolate theta 2 by itself. That will make it easier for all of us. So theta 2, sine of theta 2 is equal to n sine 34 degrees over ng is equal to theta 2 arc sine n sine 34 degrees over ng. There we go. And this would be, I'll just name it equation 3. There we go. All right. So now that we have this, let's put equation 3 into equation 2. And then altogether, we would have n equals ng sine 90 degrees minus arc sine n sine 34 degrees over ng. Putting this all together. This one's inside this sine. And everything seems to be in order. Very good. Now let's just plug in ng. N is equal to 1.544 sine 90 degrees minus arc sine n sine 34 degrees over 1.544 and there we go. Now we're trying to find n here, correct? But this n cannot be isolated by itself. So that means that we would have to use the transcendental equation method. So from there, let's substitute n as x. So we would graph it when y is equal to x and y is equal to 1.544 times sine of 90 degrees minus arc sine of n sine 34 degrees over 1.544. There we go. Everything seems to be in order. And then we graph these both onto your preferable graphing program, either a calculator or from the internet. And our intersection will reveal an x component. The intersection between these two equations would reveal an x component, which would have n equals 1.35. And this would be the max n for total internal reflection at point P. And there we go. We have our answer.